The three main kinds of degradation of biodiversity that we'll discuss are global warming, deforestation, and these kinds of enigmatic declines. The reason that I have enigmatic in quotes is that enigmatic suggests that these declines are somehow mysterious and we don't know their cause. And what inevitably happens is that in looking at these declines more and more, we find that they're all human caused declines. So, the first thing we'll talk about is global warming. And this is a very well researched subject that has a lot of sources of information, but it's actually quite simple in both how it works and why it's happening. Study after study has found a very common pattern, and that's that over the last 50 years or over the last 100 years, basically over the last course of human population expansion and technological revolution, we've seen that the temperatures across the world have been steadily increasing. Hundreds of months in a row, we have record temperatures all around the world, and you can see that these temperatures are distributed unevenly, but they are pretty ubiquitous in the fact that they are increasing. Towards the poles, we have a bigger increase in temperatures, which is not exactly good news. And the question that you should be asking yourself when you look at something like this increase in temperature over 50 years, is why? Why is this happening? Imagine you have a box of CO2 gas. CO2 gas has an interesting property in it in that it is transparent to visible light. So the light that you and I use, white light, to see, which contains all the different colors in the rainbow, that light will pass straight through CO2 gas. And CO2 gas is present in our atmosphere, and that's why at night you can see the stars so clearly. It's because that light passes right through those layers of CO2 gas. Infrared light, on the other hand, does not pass through CO2 gas so easily. CO2 gas is opaque to infrared, which is a wavelength of light that we also experience as heat. So heat energy, infrared light, when that encounters CO2 gas, it bounces off. So you might be asking yourself, how does that heat up the Earth if all the light coming from the sun passes through, but then all the heat coming from the sun, which is also light, but it's a different wavelength, if all that light bounces off, then why would the Earth be heating? Now let's add Earth to this, and Earth will be on the other side of the CO2 gas layer. When light passes through CO2 gas, of course it goes through transparently and it's not blocked by the CO2 gas, and then it continues and it hits the Earth. Well, when the Earth absorbs that light energy, it starts to heat up, and that light energy is transformed, and much of it is transformed into infrared or heat light. So that's infrared light energy that then reflects up back into space. Well, when it's reflected back up, it then encounters that CO2 gas, now as infrared, and it can no longer pass. It can no longer leave. And so because CO2 is opaque to that infrared light, it traps that infrared light and it stays between the atmosphere and the Earth. And so the result of that is an increase in temperature between the Earth and this layer of CO2 gas, which is our atmosphere. So why is this happening? Where is this CO2 gas coming from? There are natural sources of CO2 gas, things like volcanoes and other natural processes, but luckily CO2 gas occurs in different isotopes. So we can kind of tell where the CO2 gas is coming from, and CO2 gas coming from sources like volcanoes, that CO2 gas has a specific isotope. Remember, the isotope is the number of neutrons in the nucleus of an atom. So if we look at the isotope of carbon that exists in the atmosphere over time, what we find is that over time the ratio of carbon coming from volcanoes drops. That's represented by this tan line. What we find is that there's a huge increase not only in carbon, and that's what that black line is, it's a huge increase in carbon, but that carbon is carbon that is sourced from fossil fuels. This is carbon that comes from oil. And so the kind of carbon that we're finding in the atmosphere is from fossil fuels. And so this pretty much points the finger straight at fossil fuels, which is very, very clear and obvious if you just look at the trends in our technological advancements and you look at the trends in roads and car numbers and populations. It's all very consistent with the emission of carbon. You can look at North American roads, and on the left, that map is just a map of roads. It doesn't have anything else other than lines on roads, and you can see that those roads make an extremely high resolution map of the United States. And that's because we have roads everywhere. We all use cars, and those roads are being used 24/7. If you walk out of your house right now, or you just listen to the environment around you, it's quite likely that you can hear a car or hear many cars. And that's because our public transportation is mainly using vehicles and private cars in the United States. And so these roads are being occupied by cars 24/7, and these cars are emitting gas, emitting CO2 24/7, all day, all night, for decades and decades and decades. Our cars have been perfuming CO2 gas out into the atmosphere. So that's not too difficult to understand, and it's not also too difficult to understand how that might contribute to increases in carbon emissions in the atmosphere. But that's not the only source. We also use energy. To the right are the lights that are emitted from North America at night, and you can see that as a proxy for energy use, you can see there's a massive amount of energy being used all throughout North America. And much of this energy is non-renewable petroleum-based sources of energy. And so when we look at where this carbon's coming from, well, it's coming from our daily activities. It's coming from a lot of different things that we're doing daily to live, going through our natural day. You know, we drive in our car, we go somewhere, we flip on the lights, we put something in a refrigerator, and that is all contributing to our carbon footprint. But also our diet is contributing to a carbon footprint. And so if you look here, this is a map of all the agriculture around the world, and it's color-coded by where that agriculture is ultimately destined to go. So if the agriculture is going to humans to feed people directly, it's colored as green. If that agriculture is going to fuel or to feed animals, like in the meat industry, then that is colored as purple. The reason why this is important is that when you feed something like a terrestrial animal like a cow, and for food, it requires more food for that cow to grow 1 pound of meat than 1 pound of food. It requires about 10 pounds of food to get 1 pound of meat from a cow. And so this is kind of an inefficient way to grow crops. And so if we look around North America and around Europe, we have a lot of cropland. A majority of cropland is going towards producing crops for fuel and for feeding our meat-focused diet. If you look at areas in Africa, you can see there is a lot of agriculture, but most of that agriculture is going to feeding people directly. That's a very efficient use of land. And also in India, you can see that a majority of that land is being used to feed people rather than for feeding cows and for feeding meat. This would suggest that as somebody in North America or Europe, a greater portion of cropland is being used per capita because their diets are a less efficient diet, eating terrestrial animals rather than eating plants and crops directly. So what are the effects of global warming? There's a lot of different research on this, and I welcome you and invite you to use the tools of primary literature research to find all these different papers, and you can read them now that you know how to break down primary literature. If you go through Google Scholar, you can find whole swaths of research dedicated to climate science and the way that it's affected all different aspects of our planet. But I'll go through a couple examples here, very, very lightly, very superficially, by no means doing this area of research justice. But one of the main effects that I think is most important is the acidification of the oceans. This is something that we can see happens several times in the fossil record, and it's never a good thing. So when you have more carbon in the air, you have more carbon dioxide interaction with the ocean, and as a result, more of that carbon dioxide gets absorbed into the ocean. When it does that, it breaks up, and we end up with more free hydrogen ions. The effect of that is that the ocean's pH goes down, which is an acidification of the ocean. And that's a problem because it makes it more difficult for organisms that are calcifiers, that create these calcium-based shells. It makes it more difficult for them to create their shells. And so they have to spend more energy in making shells. So as a result, they're less prolific, their metabolic costs are higher, and they do poorly. If you look in the fossil record, warming events are both directly and indirectly contributing to mass extinctions. This paper in Science describes how temperature-dependent hypoxia explains the end of Permian marine mass extinction, and that is just the lack of oxygen from the increase of temperature. But on the right, we can see that this paper describes the acidification that occurred after the meteor that killed the dinosaurs. After that hit, the ocean increased in acidity at the surface layers, and you had a huge loss in diversity. You had a huge extinction event in those upper shallow layers of the ocean. In the deeper layers of the ocean, which didn't experience as much change, you actually had the preservation of a lot of organisms. This is a paper that I really like, and I think it illustrates really simply one of the challenges that we are facing during global warming. And this paper compares a mountaintop in Ecuador, both from 1802 to 2012. And in 1802, it was documented by Humboldt very clearly. Humboldt did a great job of documenting the different vegetation layers and also the limits of glacier activity and the limits of vegetation on this mountain. When compared to 2012, we can see that the limit of vegetation and the limit of glaciers went higher up in altitude. And so there's been a warming from below, and the result is that the ice melt is getting higher and higher on this mountain. On the right, you can see a graph showing all the different species and the changes in their ranges when compared to 1802 to 2012. And the green in these bars suggests that the range increased. They got higher in altitude. And you can see that an overwhelming majority of plants had an increase in range higher in altitude, which is what you would expect in a warming globe. What's important to also note about this study is that while this is looking at an altitudinal change in temperature, you could also think of it as a proxy for latitudinal change. So instead of these glaciers going up, you could think of it as the glacier line, the line of freezing water moving north or south closer to the poles. So as you have global warming, you should see the retreat of glaciers towards the ends of the Earth, the ends of these ice caps, and it will follow a similar pattern. Lastly, what if there's a species that only lives at the top of the mountain, and then the lower limit of its physiological ability then extends higher and higher? Well, those organisms go extinct. They literally get squeezed off the top of mountains, and they disappear from the face of this earth. This is a process that is likely to occur throughout regions with high species diversity in mountaintops. We laid out how global warming works quite simply, and it is pretty simple to predict. It's pretty simple to understand, and there's been a lot of confusion about how it works, and a lot of change in belief. A lot of people don't want to believe it, and there's a good reason for that. In this case, this is one of several examples of how big oil prepares for global warming, and it's had its eye on different areas where retreating glaciers will reveal new places to mine. They've also retrofitted a lot of their oil platforms to deal with rising sea levels. They've also retrofitted a lot of their pipelines to deal with more exposure because they're no longer going to be covered in ice. And so big oil is very, very aware of the future that we're going to be facing, but they continue to fight regulations, and they continue to fund the kind of destabilizing understanding of global warming for the public. And there's a good reason for that. Here in the US, we want to keep gas cheap with the intent of maintaining our status quo economy. The problem is that the true cost of gas still arrives at some point. You can imagine that when the effects of global warming occur, oftentimes because they're indirectly related, or it's thought of as being indirectly related to fossil fuels, we're no longer holding fossil fuel corporations and ourselves accountable for using those fossil fuels. So while things like more powerful hurricanes ravage the coastlines, while we have an increase in health conditions and respiratory conditions, when we have extinction events and degradation in ecological systems, the payment for that, the cost of that, is oftentimes on the shoulders of taxpayers and global economies, and it doesn't usually end up on the doorstep of big oil or other producers and pushers of petroleum and fossil fuels. That is oftentimes because the public doesn't clearly understand or clearly believe that these effects are directly a result of fossil fuels. So, in order to keep gas cheap and to avoid accountability, many oil companies and fossil fuel companies have fought regulations and permeated these kind of destabilizing narratives that prevent people from taking fossil fuel effects seriously. And at the same time, they are fully preparing for a future, an altered future that is the result and the consequence of fossil fuels degrading biodiversity and ecological systems.